Good morning, everyone. My goal this morning is to give you all a fundamental knowledge that you may already know. If so, I'll give you a refresher or some ideas and things that affect your engine bearings next time you're either assembling an engine or modifying a design or even just starting from scratch. Obviously, I'm sure everyone in this room is aware that the operational difference between a roller bearing and a journal bearing. With a roller bearing, you have continuous contact. It's very efficient at low speeds. As speed increases, your friction increases. You have less tolerance of impact, and it operates with a splash lubrication. Journal bearing, on the other hand, such as a rod bearing or main bearing, operates on a film pressure. It's very efficient at high speeds. It tolerates impacts very well. It's good for high-speed applications and requires a pressure lubrication. So as your clearance decreases and rotation increases, it builds what we call a film pressure. And as you can see here, this is a typical film pressure profile that we would see as we're evaluating or simulating a bearing. As the shaft locus starts to move off center and your what we call a minimum oil film thickness approaches, you'll start to see this pressure profile. And this here is what actually supports the shaft in motion. And similarly, squeeze film pressure is the kind of the same idea. As that shaft locus starts to move off center, it builds this oil film here, and you can see the pressure profile. Similarly, in many of you have seen main bearings or rod bearings, where you have a local point of wear or contact. That center point is the center of this pressure profile that you're seeing where you have that wear. And this is a kind of a general graph based on the different types of lubrication that you can see inside of an engine. At your boundary lubrication, this is where you have metal-to-metal contact. In a mixed lubrication, you have a small amount of an oil film produced that's supporting the shaft and some contact. And during fluid lubrication, you have full support of the shaft in motion. As your engine starts to turn over, obviously we have zero film established. As we said earlier, it takes pressure and rotation. As this happens in the engine, you can see in the different loaded areas, the shaft locus starts to move downward on the main journal, and the shaft locus is upward on the rod journal. And this is where we get to the performance factors, such as specific power output, the engine speed, bearing size, bearing material, oil viscosity, oil supply, journal shape, bearing housing shape, the entire stiffness of the system, including the stiffness of the connecting rods, stiffness of the crankshaft, stiffness of the block, and then your local balances. Back to this point right here, this is why cleanliness is such a huge factor. When you get down to 40 millionths of an inch, it doesn't take much of a piece of debris to disrupt that oil film and start to do damage to the bearings. This is a typical power curve or cylinder pressure curve, based on crank angle. And this is what we start to look at when designing a bearing. This peak pressure here is the highest point of load that the bearings will see. So that's the point that we have to be concerned about. Out of balance moments. So this is something that can also change the loading on, say, your rod bearings and your main bearings. The out of balance on the crankshaft needs to account for the reciprocating mass of your piston, your pin, and the connecting rod. If those aren't balanced correctly, then you're going to be introducing new loads on the bearings that they shouldn't typically see. And it'll affect that shaft locus center line as the engine rotates. One of these things is the connecting rod. The center of gravity of your connecting rod has an influence on the shaft locus as well as the piston and rod assembly are reciprocating. The center of gravity of the rod moves back and forth. That inertia adds an extra load on the rod bearing depending on the engine speed. And as I already mentioned, the whole assembly increases that load with your piston, the pin and clips, rings. Note, as mass reduces, the bearing combustion load increases on the cap side load. We see this typically with a lot of high-speed engines. As the inertia starts to increase, it can put extra load on the cap side of the rod bearing. And some of the data that we use when we're looking at mobility method output, and this is just an example based off of an OEM application, I believe. Looking at peak torque, peak power, and overrun RPMs, we can simulate what the minimum oil film thickness is. And here we can see we're looking at minimum oil film thickness that are less than 1 micron and film pressures of 380 megapascals. At a lower oil viscosity and high temperature, you can see what the effect of the oil viscosity does to the oil film thickness and the film pressure. We go from, at an overrun condition, we go from 0.8 microns to 0.6 microns, which is less than 3 millionths or 30 millionths of an inch, and 440 megapascals of film pressure, which is, as you can see here, almost 64,000 psi of load on that bearing. So the minimum oil film thickness and maximum oil film pressure values are changed and affected by many different things. Obviously the engine power and torque, or the load, the bearing diameter and width, the inertia and the counterweights, your oil clearance, your oil viscosity, many different things that you do as engine builders can affect the way that these engine bearings are going to perform and the amount of life that you're going to get out of those bearings. And again, to touch again on cleanliness, when we talk about minimum oil film thicknesses being about 1 micron, which is 1,000th of a millimeter, these are just kind of some common debris that we would find in an engine. Say if it's not cleaned properly, or the bearing overlay itself, the part that's actually supposed to absorb any of these materials, is usually around 15 to 20 microns thick. So when you start to look at silt particles, hair, very fine sand, these particles are well beyond the thickness of the overlay. And these are the different things that are going to cause some damage in your engine whenever it's assembled if they find their way into the oil system. Typically, there's a lot of OEM applications now are moving towards aluminum bimetal. Aluminum tends to be more conformable than your typical copper base or bronze base half shell bearings. The copper bimetal has a much stronger fatigue resistance, as well as the overlay that's applied allows for a little bit better debris absorption, conformability, and some different characteristics. Finding the right bearing material is all about finding the balance. Based on whatever engine you're building, you must have the fatigue strength and the wear resistance for longevity. But if the hardness starts to increase too much, the harder the material gets, the easier it is for seizure to occur. And that's where you start to see a spun bearing and a lot of other damage, including overlay wiping and some other bad things that can happen to bearings. Conformability and embeddability are two very important features or factors in a bearing, which you normally get with a softer overlay on a bronze part. That embeddability is very important, as we were talking about earlier, in cleanliness. If anything does happen to get inside that engine, you have to rely on those bearings to be able to absorb it and let that material embed into the bearing without causing damage to the crankshaft or excess heat into the bearing and crankshaft where you have destroyed bearing or spun bearing. And here are some differences between the aluminum bearing materials. You have a hardness here 40 to 60, whereas copper or bronze base is going to be 85 to 155. So you can obviously see the bigger difference. The copper does have a lower seizure resistance where overlay is required, and the overlay is required because of that low seizure resistance. The soft overlay, Babbitt lead material, that's what gives you the seizure resistance with the copper part. These are just some of the bearing design factors that we look at when we're designing a new part or looking at different applications. The housing diameter and tolerance are very important to determine what grading is required for each application. The axial length, the material, lug size, and location. Also, one of the important factors is what kind of oil clearance is being targeted. On the journal, whether or not the land length has fillets or if it's undercut and rolled crankshaft like we typically see with OEM applications. The material is very important, whether it's iron or steel. As I already said, the oil clearance target and the fitting range objective. So depending on how many grades that we have to set up for that application. The installation calculation, the crush height is something that's extremely important with any kind of performance bearing. This radial pressure is what's achieved by your crush height. The minimum backsteel contact pressure that we will allow for is 10 megapascals. So you see it's a pretty high amount of force that goes into the either the connecting rod or engine block housing. And this will cause a certain amount of swell in whatever housing that it's installed in. And this is just kind of a sketch of how we would typically check the crush height on a part. when a bearing is inserted into the gauge, there's a measured load that is put on the one side of the bearing surface, and that height after the load is applied is how we measure the crush height. Also, with the system design, when we look at the oil clearance and the rod bearings, again, the shape and the rigidity of the big end connecting rod is very important. As we introduce loads into the connecting rod, we see how much it deforms, and the bearing has to be able to account for a lot of that deformation. If you have excess deformation in your connecting rod, you can have close-in, which gives you contact at the parting line. You can have spun bearing. There's a lot of factors that will affect the way that the bearing performs. When we look at the clearance, the general guide is about 1,000th or 1 micron per millimeter for the journal size. If you have too much clearance, obviously this is going to affect your minimum oil film or maximum oil film pressure and your oil film thickness. As you increase your clearance, that if you remember the slide with the pressure profile, as you increase your clearance, that pressure profile actually starts to get narrow. And once that pressure profile narrows, then the load increases. And that's where you start to see some damage and other things. Some other effects, journal shape. You can have taper, convex, concave. These are things that you'll see in wear patterns usually on the bearings. As a general guideline, as your clearance goes up, your oil flow through that bearing is also going to increase. Oppositely, as your clearance goes up, you have a oil temperature decrease because that oil flow moving through that part is cooling. They're doing a better job of cooling that bearing. Load capacity. As you approach higher and higher clearances, the load capacity will start to decrease, as I mentioned with that pressure profile. As it starts to narrow, it increases the load on the bearing and obviously is going to shorten the life. And this is kind of a complicated graph on friction torque and each factor considered. This is important here with the clearance and the amount of friction. So you also have the amount of friction, basically the power it takes to spin that bearing or to spin the assembly decreases with the increased clearance. So you have a lot of things to consider when choosing a target oil clearance, and whether you go with a smaller clearance or a larger clearance, whatever you choose, there's going to be obviously a pro and a con. There's going to be good factors and bad. So it's all about finding that balance that's going to be best for that engine and best for the longevity of the engine. And then similarly with the main bearings, the block stiffness becomes important just as well as the big end of the bearing or big end of the connecting rod. Again, the housing shape change with assembly and distortion. A lot of this comes from the stud or bolt tension, and then again some of the common factors: the oil clearance, oil viscosity, the amount of leakage at the main bearing, the crankshaft roughness and shape, and again, the general guide is about 1 micron times the journal size in millimeters. Gives you a good starting point for what that clearance should be. Some of the assembly concerns that we've ran into with aftermarket engines, no bearing modifications should be made. The chamfering near the parting lines increases your oil leakage at the main bearings. The abrasives on the inner and outer surfaces can damage or embed material into the overlays. Adjusting crush height by lapping can damage the broach surface and create a out of square condition between both the parting line surfaces that mate inside the housing. And again, cleanliness throughout the entire system is very important.